So, the paper that we're going to be that I'm going to be presenting today is DreamCoder. The full name is this ridiculously long one: Growing Generalizable Interpretable Knowledge with Wake-Sleek Bayesian Program Learning. So this is work done by Kevin Ellis and his collaborators, and I am just presenting it. Um, so the main question here is, what is this idea of program induction that this DreamCoder uses? So the idea behind this is you are given some task, and this task is usually defined as input and output examples. So in case of the task where you're sorting, you might be given a bunch of lists of numbers and the corresponding sorted versions. And so the task of program induction is to generate a plausible program that solves the task. The reason why we do plausible here is because there might be multiple ways that you could solve a particular set of input and output examples that might not actually solve the real task. So in case of the sorting algorithm, I may give you only 3 input-output examples. And so you could just hard code essentially a hash table that, given this input, return this output. And that would be a program that plausibly solves the task given these examples. But when you would be given more examples, you'd see that it fails. And so that's why we have this idea of a plausible program, as you don't know 100% sure whether or not the program you generate actually solves the task. So why even want to do this idea of generating programs? Well, programs actually have this kind of nice, some nice properties. So some things that Kevin Ellis highlights is that you can represent knowledge as programs. Essentially, the knowledge of how to sort numbers, or what even is sorting, or even more abstract ideas of like equations. You can even think of those as algorithmic steps that you have to do to determine the force of gravity or something like that. You can think of these programs that just do these basic steps as representing knowledge. And the idea of learning this knowledge is essentially just adding to whatever set of programs that you have. So creating more programs means that you are adding more knowledge, therefore you are learning. And so this is the way that you can go about making new programs is this idea of program synthesis, which uses this program induction technique. Also, if you're able to write a program, depending on the program, it can be generalizable. So if you can actually write the correct sorting algorithm, it doesn't matter if you're using, lists of length, 5. You could apply the same algorithm to lists of length 7, and so they can be generalizable. Also, you can usually interpret programs a lot easier because they're just compositions of simpler pieces. So for something like sorting some lists, you have to first iterate through the list. So you could understand that you're going through each element. And so dealing with programs and having these as sort of your idea of knowledge makes it a lot more interpretable, the knowledge that you have, at least to humans. Also, from Alan Turing, he showed that these Turing machines, your program is sort of written to perform computations. Then you get these basic universal solvers that you can solve essentially any task as long as it's Turing complete. And so how do we do this program induction? So current techniques that have been the most sort of useful is this idea of Bayesian program learning. So what is Bayesian program? So the definition given by Kevin Ellis is the system learns both a prior on programs and an inference algorithm, which can be approximated using a neural network, to efficiently approximate the posterior on programs conditioned on observed tasks. Now, what does that mean? So mathematically, I think it makes a little bit more sense. So you create a generative model. This generative model is just a probability of some program that solves the task, given whatever the task is. So that's what this X is. In the paper, you'll see just X's everywhere, and this just means it's the list of input outputs. So what is the probability of a particular program? Given the input output examples, and then whatever pieces of computational logic like ifs, conditionals and stuff make up your library that you can compose into a program. So this program is made up of different pieces of this library. And so this is saying that I can have a probability distribution on the different programs that I can make given some library and some task that I have. And so in general, what you can do is you can approximate this with a neural network. Now, to be honest, this paper was very sort of high level. It didn't have a lot of details. And so I found it very difficult to actually understand whether or not their actual approach approximates this with a neural network. I read the paper top to bottom and I still couldn't figure it out. But in general, at least what I've read in previous literature that's done this is that they use a neural network. Okay, so let's get down into an example of what sort of inspired or how this idea sort of works. So we have some initial primitives. So this is your library, or what they refer to as L. And this just contains a bunch of different operators, so map, fold, if, const, greater than, or less than symbols and stuff like that. And what we want to do is we want to take these and assemble them into a program that solves this task of sorting lists. So the sort of question proposed here is, how do we compose primitives on the left side to solve the task on the right? Well, what we could do is we could just search through all combinations of the primitives. So, we're going to take a map, and then we're going to apply a fold. Then we're going to do an if, and then we're going to do a const. And we're just going to find all the combinations and just select the one that actually gives us the correct output given a particular input here. And also, one thing that we're going to want to sort of how we would rate each program, because there could be multiple, is that we want it to be as short as possible. So the shortest program that could possibly that we could possibly generate through this search that solves these examples. So let's do that. All right, so this is what it looks like. It's extremely long, completely uninterpretable really to a human, because they use this very special lambda calculus programming language. And also it took approximately 10 to the 73 years, which this is like way past the heat death of the entire universe. And so it's not very practical. And so you might wonder, like, how did they even generate this if it took until the end of the universe to compute? Well, they acquired useful abstraction libraries to actually solve the task that were later related to the task. Now, what do I mean by this? So essentially, instead of only dealing with this initial of primitives, they combine these primitives into useful concepts where they term useful here as you use it a bunch. So if for software engineers, this is you want to be able to do code reuse. So you might want to, if you had to are copying and pasting a lot of code, you might refactor whatever code snippet that you're reusing a lot into its own function, and then you just call that. That's essentially what this idea of learned library of concepts is doing. If it finds that it needs to apply this particular fold and other types of primitives together a bunch. So this particular concept, which actually ends up being the filter function, well, then it just collapses that all into its own primitive that it calls it. So this new primitive is just a collection of all of these other primitives. And so it adds that to its list of concepts that it's able to choose from. This dramatically cuts down the amount of searching that you have to do. So instead of searching every time for having to add this, lambda symbol here, then a fold, and then you have to do this nil, you can just say, okay, the option that I'm going to pick next is just this concept 4. And so you can drastically reduce the amount of searching that you have to do considerably. And so this concept 4 is essentially the learned concept of filtering a list. Another concept that the model learned during its training of trying to solve this task was this maximum concept. Similar idea, so it just essentially took this filter and a few other initial primitives to construct this maximum function. And then lastly, it found this nth largest element concept, which took the concepts 13, which is the maximum, and a few of these concept 4s to find the largest element. And it made it into its own function call, basically. And then it uses this finally to generate this solution. And so, as you can see, this is a lot more compact than the previous one that we had here. So if we were to unroll this basically and only write concept 15 in terms of primitives, we would get this huge one. But since we were able to sort of cut through those individual steps where we'd have to redo our program search on each individual primitive here, we were able to actually cut down the amount of sorting that needed to be done, because instead of having to search for this particular character, then this character, and et cetera, we just had to find the concept 4 and then select that one. And we got all of the other program operations for free, since this concept includes all of those. So we were able to, they were able to do this in 10 minutes versus the 10 to the 73 years. So how does this work? How do you grow? So basically the big takeaway from here is that we want to grow this learned library of concepts. That's basically the whole approach. That way we can cut down the amount of searching for the program that we have to do. And so that's the main goal of this paper, is how to learn these concepts. So DreamCoder uses this wake-sleep sort of algorithm. So in the wake version, they solve problems by writing programs. So in this case, they actually just are given a bunch of real-world tasks, and they apply their current set of libraries and neural network for selecting which program to predict next to solve a particular problem. Then in the sleep, they try to improve the library and essentially extend the library with these new concepts, as well as train this neural recognition model to perform better. And so the sleep phase is broken down into 2. So abstraction sleep, which improves the library, and then dream sleep, which improves the neural recognition model. And so I'm going to switch just to show this visually what this looks like. Switch to the paper. Nice diagram of this. And so this is the sort of algorithm. So here they have this wake phase. So they're given some set of tasks in the current library. And the task here is fed into the recognition model. And it helps by biasing the neural guided search of the programs that you're going to choose based on the library. And then you just essentially select the best program that solves given task, which is basically just pick the highest probable program, which is approximated by this neural network. I think they aren't very clear. And so in the sleep abstraction phase, you essentially, all of the programs and stuff that you got right here that actually solve the task, what you do is you look through and you find useful, and the way that I think about it is useful code snippets. So ones that you use over and over again. So here you can see that they use this +1 operation over and over again in multiple different programs. And so they compress that, they refactor it into its a new library routine. And they readjust all of the probabilities using this formula here, which is just basically using the update rule for Bayes theorem. So they are able to compress all of these programs and generate the new probability for what this program is using Bayes' rule. And then and honestly, this sleep extraction and this wake phase, this was actually done in a previous paper. The new part, as far as I can tell, is this dreaming state. So this dreaming state is where you sort of train the neural network to do better at this guided, neurally guided search. And so the way that this is done is through these fantasies and replays. So I'm going to quickly switch back to here to sort of go over a little bit more in depth of what each one of these steps is. But essentially, in the wake phase, this is where you generate the programs, this whole task. And here I show that it's a little bit unclear exactly how this is done, but to the best of my knowledge, this is how it works. They use a neural network that takes in these inputs and outputs examples and a previously generated operation, and they essentially predict the next operation to perform in the program. You have your inputs and outputs here, and this is sort of the tree of decisions that the neural network goes through. So you start off and it selects this particular operation because it was the most probable to come next. And then it might have another operation that it could choose, and it might follow that line because they use beam search. Since this one might be super more probable down the line given this one. But say, for example, that this is the next most probable operation to perform after this one for the program. And then lastly, to solve the program, you redo this particular operation. And so the neural network basically just selects from all the options, which options are best to take to solve a particular task. And these operations in the order in which they are selected just become the program. So in essence, the neural network is saying, okay, first run operation 1 on the input, then operation 3 on the input, then operation 1. And that's how you get to the output. This abstraction phase is where you actually grow the DSL. DSL is just domain-specific language. They like to mix and mingle the different terms, but essentially this is just the library. And so again, it's just this idea of compressing the found parts of a program that were commonly used together to make a new concept. And it uses a bunch of complicated heuristics that they actually don't really discuss in the paper. I believe they discussed it in the previous paper, but I haven't had a chance to go through that one. Okay, and in the sleep, in the dream phase, I think it's a little bit easier to understand just from text than from the image. But essentially what they do is they sample programs from the library. So these are just random programs, as far as I can tell. There might be some bias that they use to do this, but they aren't very clear on that. So in essence, instead of having the model select which of these operations to perform in the program, it's just randomly done. So you might start from this operation, then go to here, and then you might select option 2, and then 9, etc., all random. And that gives you a random program, but this program is at least like functionally correct. You can give it some inputs and it will generate some outputs. So you create these fantasy programs that don't really have any set tasks because they're not real world examples. They're just randomly generated programs. And then you select inputs that you feed into these randomly sampled programs to get their corresponding outputs. Now you have the input-output pairs that define the task, and you can now train the neural network to give the highest probability to the sampled program that the input and output came from, since you now have the ground truth of the real sampled program and its inputs and outputs. And so you can do a similar process, and they do, from instead of fantasy programs, but from real world tasks that were seen during the waking phase. And they call these replays. All the learning is done using this map inference algorithm. And essentially what this tries to do is just maximize this particular equation here. So what this says in essence is that I want you to average the performance of our neural network, which they define as Q, for the given, for the maximum probability assigned to a particular program or whatever task. And so this is essentially trying to bias the probability of the best performing program that solves a particular task, giving some library for the model to learn. But you have to do it across all of the tasks. So this tries to, which is what this expectation is, it's taking the average essentially. And so you're trying to increase the average performance across all of the tasks, both fantasy and the replayed ones of this neural network. Okay. And so, okay, so that's basically the idea. So you just keep running through these different cycles where you go through a wake phase and a sleep extraction phase to add more library tasks or library concepts. And then you do this dream phase, which trains the neural network to be better at predicting the programs. They evaluate on a bunch of different tasks. So the sort of three main tasks that I list here are like the main ones, from what I could tell. They do some other tasks, which I'll mention in a bit, but they're more ad hoc generated. So some popular ones in program induction is this list operations. So this is things like sorting, reversing, a bunch of different types of list operation tasks. And so there was 218 problems, and they had 15 input-output examples for each problem. So very small amount of data. And they split it 50-50 between training and testing. The interesting thing is, the program could basically solve all of the tasks, all of the problems once it was trained. But interestingly, the concepts are the new library concepts that the model generated were very human interpretable. So it created 20 new libraries to solve all of these tasks, and it discovered things like the filter function, find largest nth elements, and things like that. So it recreated like some stuff from like a standard library that you'd see in a programming language like Python or something like that, just from these very basic primitives. They also do a very similar idea, but for text editing problems. So this is, convert this one sentence to another. So you might see this in Excel, where you want to basically only use the first letter of a person's name. So you have to write a program that takes the person's full name, but then shortens it to just have the first initials of each of their names. Similarly, they had about a 50-50 split for training and testing, and they were able to achieve 49.6% accuracy, and it only took them about 40 seconds to solve. This is on par with previous ones, which got a little bit higher. I believe something like 86 percent accuracy, but they needed an hour to do the solving. So they're way better. And when you give the model about an hour, so the difference between it is like 0.1% between the accuracy of the DreamCoder and the hand engineered approaches. And those hand engineered approaches, they wouldn't be able to be used on this list ops. So it's very general, this DreamCoder. They also have this image generation task, which looks really cool. And essentially the model, after being trained on these images, can do different types of, it learns to draw different types of objects, such as circles, squares, different types of spirals, which were not in its original library. So some of the tasks it learns are pretty cool. Okay. So this is like one of the tasks that you're required to learn how to do. So they're kind of complicated, different sort of objects here. And what the model learned to do is it learned the semicircle function. So you give it some radius and it learned to draw the different lengths. Similarly, it learned a circle function, a spiral function, a Greek spiral function, an S-curve, and a polygon. And it was not explicitly given how to do this. It was only given like originally in its library, you can put a pin at a particular coordinate. You can move the pin in a certain direction to like draw it across the screen, and you can pick the pin up. Like that was some of the like the most basic. Oh, and you could do like a slight curve. That was all of the instruction that was given. So it built up these additional semicircle one, circle one spirals and stuff like that based off of those very small primitives. And you could even do like these radial body ones, which are like super complicated looking. These images here are the dream phase, which is the sort of random programs that get generated, which are sort of biased by the model, it seems. And so at the beginning, you can see that it's generating sort of just like really basic looking programs randomly. But at the end, once it's fully trained, it starts to combine and dream up fantasies that are extremely diverse and like complicated, showing that it sort of is able to get better and better at synthesizing these just like fantasy programs. There's an, okay, so that's for those tasks. There were a few other tasks that were interesting. So this block placing task, which is just basically copy and paste. So if it was given a tower like this one, it could reproduce that tower. So it was very simple, like copy paste example, but it learned things about how to create arches, how to create walls, pyramids, bridges, all this type of stuff. And here's some of the imagined stuff that it could generate. So here you can see sort of like random the way that it constructs the blocks, but at the end it's hyper specialized the dreams that it can come up with to tasks that it might see in this. In trying to solve this task. This also did some regex ones, so it could learn to generate regexes for phone numbers, dates, times, and money. It was also able to infer real parametric equations. So this is, like, 1.2x subscript 1 plus, or sorry, just today, like 1.7a plus 2.7b plus 3.7x or something like that. It was able to generate that function based off of just examples that it would see from that. So it could generate rational or polynomials up to degree 4 functions from examples just generated by the true function. And it could do the same thing. So like if these real values that were generated from a true function, if it was like a particular physical law, so like Newton's law or Coulomb's law, those types of equations or other mathematical identities, it was able to infer the actual equation that it came from. So they have a nice description. So here. So starting just from these very small primitives of like map, zip, const, empty, and stuff like that, you learn how to subtract vectors, add vectors, and then do sums of vectors. So like doing, you could even do like square roots, all these complicated things like dot products and stuff like that, inverse square as well. And so it can combine these concepts and stuff to generate like Newton's second law, so which is just a scale vector, the reciprocal of m, and adding many vectors together, so the sum function. And it could do this for a bunch of different ones. Figured out work, kinetic energy, Coulomb's law, all of these types of ones. And they even tried this with like one of the more basic programming languages called Lisp. And they showed that it could generate even recursive programming algorithms using this Lisp set of functions, primitives, and stuff like that. Okay, so that's sort of basic end of that. Here are some questions that I sort of had while reading the paper that I couldn't really find answers to. So one of the questions that I had was, how are these fantasy programs sampled? Like, is there a probability distribution on the libraries of the operators? Does the neural network come into play here? Also, is there a limit to the number of newly composed library operations the model can learn? So this one's interesting to me because they say like, oh, the model was able to learn like 20 new concepts when it was learning the task for list operations. But could it have done 21 or whatnot? Because to me, for the neural network to predict like what the most probable next operation to perform, this is going to be like a very large vector of where the model says, okay, I'm guessing 20% is going to be on the concept 4 or something like that. And so if this vector here has to dynamically change, I don't know how that's actually done, or whether or not there's a fixed sized, sort of like a vocabulary, where you have the library functions that you give the model, so extremely basic, and then the rest of it the model can fill out itself. They don't really discuss that, so that was one thing. Like, is there upper limit on the amount of functions that it can add to its repertoire? Some interesting ideas that I had is like, can you use this idea to generate a tokenizer using the similar approach? So you give it like basic Unicode characters, and then sort of like what BPE does, but in this case, the model learns to generate more useful tokens that it uses more often for a particular task. Also, could you do something this for like a higher level language where these like new concepts that it builds are essentially like code snippets? So instead of having to predict, one token after another, it could predict an entire code snippet since it added that into its sort of knowledge base, its repertoire of libraries it can choose from. And then there was another idea where why not use a separate model for generating these fantasy programs that are potentially better to learn from? So this is sort of in the idea of like a GAN or something like that. So you generate programs, these fantasies that that instead of sort of this random style programs, but the fantasies are, you generate them in a more targeted way that might help the model learn. And so those were some of the interesting ideas that I had reading the paper. That basically does it for this presentation. So if y'all want to, we can now discuss it. Everyone, if you have any questions, let me know.
This was a really good presentation. Thanks, Nate. Um, I also had like similar questions to the one you had towards the end of the presentation. Mainly like how it changes like or how it modifies the general machine learning pipeline of like, okay, we have a training and a test set, but since their data set is small, obviously they try to synthesize things, which is the fantasies phase. But it was really interesting that although they had very limited data, they were able to dream up or like generate or sample some way to generate new programs or new problems that the model hasn't seen before, and that um, really helped like the model understand better what it's supposed to do. Um, Towards the end, we saw like very complicated figures that normally a human wouldn't make. So I thought that was really interesting.
Yeah, I thought that was
Um,
really interesting as well. It's almost like they called it like curriculum learning almost. So like the fantasies that are produced at the beginning were super simple, and then it would progressively get harder and harder. And that the reason why it might do so well is this curriculum learning.
Gotcha. I'm not familiar with. I've heard the term, but I'm not familiar with like I guess how it works. Is it just like progressively more complex?
Yes, exactly. So just like in a like course or something, you don't start immediately off with, all the fancy, calculus 2 or something like that, doing, double integrals and all that stuff. You start off with basic stuff, you learn from that, and then you move on to something that's a little bit more harder than that.
Good to know. Good to know. Yeah. Um, yeah. I wonder if this is like. It seemed like the DSL they're using is super low level, so something like assembly. Um, I wonder if yeah. A question I think you also brought up was like uh, something. Do we want to? Would we maybe want to generate a model that would do this for higher level programming languages like Python, where concepts are usually in one snippet. Um, Another thing to think about is um, I lost my thought. Yeah, I think multiple models, if we are to expand it to higher level programming languages like Python, or to solve like I guess more complex things, um, maybe a hierarchy of concepts might be necessary. But also concepts can be expressed in natural language. Here we focus a lot. The paper focuses a lot on the input and output samples. And repetition in the input code or input programs or input logic. Concepts can be expressed in natural language, and something I'm thinking about is like, can we learn these concepts from the relationship between code and natural language itself, while needing like less samples? But can we learn more diverse concepts? Um, yeah, I guess if we feed it assembly, it could learn concepts, but if we feed it something more high level, it can learn maybe more complex concepts. Um,
Yeah,
Yeah, wonder how we can yeah, go ahead.
I was just saying they don't start from assembly. They do start from some kind of complicated functions. So like this map function, this fold function, conditionals and stuff like that. I get ifs and conditionals and stuff like this assembly, but it's like map and fold and stuff like that. Those are a lot harder. And I believe they did experiments where they like left some of this stuff out, and you aren't able to get. It's a lot harder for the model.
Oh, good to know. So something good to keep in mind is like how long can these concepts be? How long can it tend to, I guess.
Mhm.
Um, yeah, thank you for sharing. Yeah, I didn't note that. Thank you for bringing that up.
Arta, you have a
Yeah, so
question?
as the training progresses, we kind of get to uh, more complex concepts, right? And there is no like principal upper limit for that, as if we can grow the library uh, like arbitrarily large, and if we, if the high level concept will be useful, like reusable, right?
Mhm.
Then we can kind of create a Python like
Yeah,
further down the path if it's really useful, right?
yeah, yeah. Yeah, that's an important point. The concepts that they generate, I keep forgetting where the figure is. concepts that they create. So this is where the new concepts are generated from, and they are only done from the waking phase. So they don't actually learn any new concepts during the dream phase, which I found sort of interesting. I guess because these fantasies and stuff aren't really based on real tasks. And so perhaps learning concepts from these fantasies and stuff would sort of pollute the library. But I feel like if you could make these fantasies sort of better, more realistic maybe, or something like that, then it might be useful to apply this abstraction to also these fantasies.
So the main goal of dreaming phase here is to improve the neural network, which we use to guide the search, right?
Correct.
And that's kind of orthogonal to the phase when we compress the library, right? So we need to run this in turns, like to keep the neural network updated, right? So it can really use provide the useful scores for the newly created concepts, right? We need a dreaming phase after each compression phase, right? So that's how it would kind of roll here, right?
Correct. But
And
one interesting thing is that the new concepts, they don't start with like a probability of 0. You can apply this Bayesian rule to get what the probability of all the combined parts are. So they don't immediately start off with 0 being there. But definitely you need to do the dreaming phase after the abstraction phase so that the model can reattune the probabilities of these new concepts. But they don't start off with 0, else the model would probably also suck.
yeah, so what would be exactly this P of rho given L? So the second component of this part. So the first component is like a probability of solving a task given a problem, right? And that can be either like binary if we have like this list task, right? That can be either solved or not solved, or if we have some kind of, if we are trying to solve some kind of approximate, find the approximate solution for a task, then it can be continuous, right?
Correct.
And what about the second term?
So this one, I believe they call it the I forget exactly what term this is, if this is called the likelihood or something, or if this is called something else. But this is basically what is the probability of the program that we can generate given the library that we have. So this is to make sure that the programs are small and not like overly long. So you try and, this is sort of forcing it to have the program be tiny, because this program is made of multiple different pieces from L, multiple parts from L. And so this is basically saying, like, what's the probability of me getting to this program by assembling all of the concepts from L? And so if you have to assemble a ton of parts or concepts from L, the probability of this program getting generated is smaller. So longer programs tend to be smaller. So it's sort of like a normalization factor, almost.
Oh, so it's kind of like encoding our assumption that short programs are good programs, like
Correct.
that, right?
Correct.
So it's kind of like the Occam's razor, like simplest solutions are the best type deal, right? Because I was looking for where they kind of forced the generated programs to be of a shorter length, but I guess this is where it is.
Yes, that's actually a really good way of looking at it. Yeah, it's essentially trying to apply Occam's razor.
Great presentation, by the way. One question I was going to ask is like, okay, so initially they're adding these primitives to the library, but there's no guarantee that these primitives at the start will be like useful in any way. I don't think. And so this is initially then adding loads of primitives to your library. So your library's growing bigger, but you're not actually getting anything useful. So wouldn't that like increase this amount of like search space time? Because I couldn't find it anywhere either if they like pruned the library at some point to get rid of primitives that weren't used often. Maybe I missed that.
So I think the way that it works, they don't discuss this, but the reason why it works is that these new concepts are only built from when they solve a task. So this compression is only on programs that solve tasks during the waking phase. So they were given a bunch of libraries, a bunch of tasks. They generated a bunch of programs. Those ones that solved the task were added to a particular list. And then commonalities among the programs that solved the tasks were then condensed and put as their own concept. And I guess that is how they ensure that the new concepts that they're learning are, quote unquote, useful. Um, and why they don't even do it during the fantasy programs that they learn here, because, as you said, it might, generate unuseful programs or concepts that just dilute the library.
Yeah, and then my other question, I think very similar to one you had, was these outputs during the sleep phase are like fantasies, I think, where it generates its own problems. These become more complicated over time, but this is only because it's adding new functions to the library, right? There's no like method of increasing the diversity of these things over time to make them more complicated. It's kind of like the curriculum learning thing someone mentioned earlier, I assume.
I mean, so that's where my confusion comes in because I don't actually know how these fantasies are generated. To be honest, I don't even know 100% how they generate these programs because they're very loose. The way that I understand how they generate the programs is that they approximate it with a neural network. So the neural network says, okay, pick this program next. But when they talk about this dreaming phase, they don't actually say that they use the neural network to generate these fantasies because the neural network needs a task in order to generate the fantasies. And so I mean, I don't actually know how they do the sampling. It's very weird because when they talk about generator, the only thing that they refer to as generator is this library of functions. They call this their generator model. But in the previous paper, they say that they approximate this generator using a neural network. So it's very confusing, to be honest. I don't know where um, the neural network ends and where it starts, um, and how these fantasies are actually generated. I'm assuming that somehow they are using the neural network, um, but they just say that they use it randomly. But to be honest, I really don't know. It was one very confusing part of the paper.
And I also, I guess one thing I thought about was like, there's no really mention of like reinforcement learning because I've seen this type of stuff done with reinforcement learning used to like guide the search space. And this is like similar to what like AlphaGo does, right? It has this like tree of searches and you prune it using whatever. But if you like Control F reinforcement learning, I think there's one in the references, but that's it. And it's not really relevant that way, but I just thought it was interesting.
I got that as well. And I got that impression from Yannick Kilcher's video on this paper because that's what he says. He says that they use this reinforcement algorithm from like AlphaZero or AlphaGo. But reading through the paper, it doesn't seem like they do that. They use this thing called map. So they maximize the training of their neural networks, which they call Q, which makes you think of Q values and Q learning, which is reinforcement learning. But they do this map inference. And so they don't actually use reinforcement learning. At least they don't model it like a reinforcement learning problem. And so I'm guessing Yannick just assumed it was. Or maybe this map inference is like comparable to some sort of reinforcement learning, but from what I understood, they are using an entirely different process. Maybe they're equal to each other in some way, but yeah, they don't at least talk about it in the context of like Q learning and doing this sort of reinforcement learning paradigm. I'm hoping a lot of these questions are probably answered in their original paper, this library learning for neural networks, because this DreamCoder one just extends that previous one with this dream phase. I'm hoping that a lot of it is discussed in here, where they call it ECC, or EC squared. But I haven't had time to read through this paper for this presentation.
So wait, the previous paper didn't have the dream phase, so there was no like generation of programs, fantasies.
Correct. You can actually go quite far because they do an ablation, I believe, where they remove like the dream phase or the abstraction phase and see how it performs. Maybe in their supplemental material. But without the dream phase, you can still learn all of these problems. It just takes a lot longer. The model doesn't generalize as fast. So this dream idea is just an extension of their previous work, from what I could tell.
So I watched the author's presentation recently, and there was a question regarding like this in this ablations. There are results showing that dream phase is like very important for solving this problem, and so the author said that basically this is kind of the relation between importance of the dream phase and the abstraction phase is kind of arbitrary, and for this paper they focused their attention on dream phase more, and in the previous paper the abstraction phase were had more impact during the ablations, and yeah, that's kind of
Interesting. Yeah, I had gone through some of his previous presentations. That's where I got some of the slides. Like I saw some ideas from his slides. But yeah, I don't think I stuck around for the questions. That's good to know. I wonder why there's such differences between the two papers in the ablation. Any other questions?
uh, if anyone stumbled on an application of this approach to the abstraction and reason challenge, which was the Chalet, I think like about 1.5 years ago or something. Those tasks with like complete the image task.
Yeah, that one was a cool one. The art challenge. Yeah, it seems perfect for this type of stuff. I haven't heard of anyone using it, but it seems perfect.
I think it would be interesting to try it out and yeah, like to really understand how this work. Uh, I, I'm not sure. I think like they had a Kaggle competition.
Mhm.
See, and I'm not sure if that was a subset of the tasks or something, and how it progressed from there. But I wonder if it company with like winning competitions, uh, winning approaches there, both kind of in terms of performance and conceptually.
Mhm.
Did people them synthesis approaches and like what gave the best results?
Yeah. One thing I found
Is there
with
an implementation of this anywhere? Or
yeah, they
sorry.
have a GitHub. No, you're good. I've been wanting to recreate it, re-implement it like a simplified version. But they do have GitHub with all of their code and stuff, so you can re-implement everything. So that's probably the best way to answer some of these questions on like how the fantasies are generated and all that stuff. Because I'm guessing all of that stuff is there.
And it could be a cool project. Happy to participate if, for example, just to try to like recreate the ideas, maybe not the same, and apply it to the arc challenge, and maybe there are some like things one could try, like to swap the building blocks. For example, in the same presentation I mentioned, that was the first author was talking about. They used some kind of bigram model for the like the skew model here.
Yeah.
Is what was some kind of bigram model, and but like conceptually you can use anything here, and maybe you can merge it with something like decision transformer, or yeah, like any kind of like scoring function for the and also on this part of abstraction, like they say there is some very complicated well, at least complicated enough not to go into the details in the paper. For the abstraction phase, this like choosing the most useful like parts of the tree here, and if you kind of like probably one can try to use a graph neural net to on the like program graph, right? So that's a tree-like graph structure, and there are like approximate methods for frequency of graph mining, right?
Yeah.
Yeah. So how it impact on the performance? Would it like can one kind of get something to make it work better or stuff like that? Really?
Yeah, I like that idea a lot of using a model to do the subtraction of the compression. Yeah, I mean, a graph neural network seems perfect for that type of thing. Um, that way you don't have to use this. I'm pretty sure they use a very complicated like heuristic to do the compression. So having something learnable uh, seems incredibly useful. And maybe you can even, do this idea of, curriculum learning, where the model, compresses more and more, or compresses things that are higher and higher level, the more that it's trained. throughout the learning process. But yeah, I mean, I think this approach can be extended to a bunch of different sort of domains. I'm sure there's a lot of technical details that had to be worked out, because even when they're like, they call it a general approach, but there's a lot of stuff you have to do to get the approach to work for each individual task, like list operations versus text editing operations versus the formula generation one for physics. So it's there's still a lot of handcrafting stuff that you had to do, a lot less than all the previous approach. So I'm very looking forward to seeing extensions to this work.
Finally, I was wondering if there are kind of any kind of approximate task they tried. Because it seems like all the tasks are like binary, right? So the solved there is a single correct answer for task. And it would be interesting to apply this kind of approach to approximate tasks, I guess.
Yeah, I believe the regex, I didn't fully understand, but they said that it was like a probabilistic regex or something like that. So I think that one wasn't exactly binary, but I'm not 100% sure.
What I'm thinking is this, for example, this like reconstruction of physics laws, and for example, there are like research in like control domain to apply to identify the like linearized approximation of the dynamic system. And here it seems like there's all a similar task, right? You are given a bunch of numbers generated by a function, and you want to find the underlying function, right? But in that case, you might not need the exact function, which might be really very complex, right? But you might be happy to get simplified but like accurate enough function for data generating. So that's one like approximate thing I'm thinking about.
Gotcha. So the program that you generate is a probability program, a probabilistic program. Yeah, I like that a lot. All right, well, I'm going to have to wrap up and start leaving. I'm going to have to do some errands, but yeah, this is probably one of my most favorite papers that have come out recently. I'm really think that at least this sort of thinking of like program induction, this sort of dreaming idea, is like a huge step. One of the bigger steps that we've had towards like general intelligence. Way more than the like GPT-3 style, just read the world kind of ideas. Yeah, and it was very complicated paper. I definitely would like to read this second one to see if they have any more ones. But it was a very fun paper to go through.
Thanks so much for the presentation. That was really good. And yeah, I hope we can start some kind of a small project to recreate bits for this approach.
Yeah, that would be a good idea. Especially like simplified versions of them. Well, I am going
Yeah.
to
Thank you.
go ahead. Sorry.
Oh, no worries. I don't know if my mic is working. I'm on my laptop because I was moving and I still didn't assemble my desktop. So hopefully I'm clear. Because I've been using this laptop for like all my meetings. I think it would be good to just try and recreate. I skimmed through some of their code. It's it's very object oriented, which is good. but also I couldn't find like how they sample stuff because I was also interested in that. So re-implementing it, or like it would take a while, I think, to find. Um, but yeah, it would be interesting to build on this work, and definitely I agree with like this is good in terms of building some sort of general intelligence because it's able to do well on different tasks, and the abstraction component is necessary for intelligence. And I really like that. I guess the field of program synthesis is working towards that as well. Um, yeah, and hopefully it can help our work.